Okay, last time we discussed the t-test as a way to compare two groups. And Anova, or an analysis of variance, is very similar. It's just that instead of two groups, we have three or more groups. And so there will be a few more steps, but I do think that it's helpful to kind of walk through this procedure so that you can understand better kind of conceptually what it is that we're doing, and you can see the common thread that connects these procedures across these different types of analyses. So I have a simple data set here to the right. I thought our hypothetical example could be that we have my class for statistics, and let's say that in this hypothetical world I only have 3 students. I kept the data set here small so that it's not too overwhelming for us to do these calculations by hand. So I have the end of semester grades for the 3 students in my class in statistics. So one student made a 90, another a 94, and the final one an 89. Then I have 2 other sets of instructors. So for other one, this instructor, their students had scores of 85, 89, and 90, and then 80, 85, and 88 for the third and final instructor. And so as you can see, we have 3 groups, right, and a total of 9 participants overall, or 9 students overall, 3 per group. So the first thing that we want to do is to construct our hypotheses. So our null hypothesis, very similar to the t-test, is simply that the groups are the same. That any variation that we see in group means here is just due to random sampling variance. Or more specifically, what we're saying is that all 3 of these groups are random samples drawn from the same population. There's no significant difference in grades between the 3 instructors. Right? So we're simply saying that there's no significant difference in sample means. Our alternative, or our research hypothesis, would be that they're not the same, that there are significant differences between the means of these 3 groups. So here, sorry, I should put no significant difference. And here we're saying that yes, there are significant differences between the means. And so each of these instructors, it may represent different populations, or at least that one of them is drawn, one of these groups is drawn from a different population than at least one of the other groups. So it doesn't necessarily mean that all 3 of these are drawn from different populations. We could say, and what I might try to argue from a more real world stance, to argue that I am significantly different, right? That my students are drawn from a different population, students who make better grades. Likely, I would make the argument because I'm such a great instructor, right? And so I may not be too concerned here that there's differences between other instructor 1 and other instructor 2. I might simply say that these 2 groups are drawn from the same population, but from a population that is different and has a different mean than the group here for me. So just like we did before, we want to compare these 3 groups. And our research hypothesis is that at least one of these groups is significantly different. The mean of one of these groups is significantly different from at least one of the others. And so we'll have a few steps here, but a couple of things that we'll want to do is first calculate means. So we'll want to get group means for each of my 3 groups. I'll also want to get what's called a grand mean, which would be the mean of all 9 of these scores. So I'd add all 9 of these together and divide by 9 and to get my grand mean. I will also want to calculate my degrees of freedom. And because Anova is a little bit more complex, I have several different measures for our degree of freedom. So I would have a degrees of freedom measure for my within group comparison, my degrees of freedom for my between groups, and then technically I would have a degrees of freedom for the total, which would just be the sum of these two. I would also want to compute what's called sum of squares. So again, I would have sum of squares within, sum of squares between, and then sum of squares total, which would just be these two added together. I would calculate what's called my mean square within, my mean square between, and I could calculate my mean square total, but we won't be too concerned with that because I will use my mean square within and my mean square between to get my F statistic, which just as we did before, I would compare to an F critical value that I get from the F table using now my two measures of degrees of freedom and my alpha level that I decide upon. Right? And I will compare the F statistic that I've calculated to the F critical value. If the F statistic that I have calculated is larger than that critical or that cutoff value, then I would say that I've supported my research hypothesis that at least one of these groups is significantly different from at least one other one. Right? And I would reject my null hypothesis that they're all the same and that there's no significant difference between the means of these three groups. All right, so let's go about calculating some of these values. So the first thing that I'm going to do is to calculate the means for each of my groups. So I take each of these three values for my group here, 90, 94, and 89. I'll get my sum and divide by 3. So the mean for my group is 91. I would do the same for each of these other groups. Each of them has an N of 3, so the mean here is 88. And finally, we have, as our last group, mean of 84.33. And so it does look as though if we look at just the means, that the mean of my group is higher than the other two. But if we look at these two here, you can see that it's pretty close, 88 compared to 91. So we're trying to see, is this difference here greater than what we would expect due to chance or random sampling error? Does this difference represent a true significant difference between the groups? So another thing that I'm going to want to calculate is what we talked about here, this grand mean, which is the mean of all 9 numbers. So I would take all of the grades for this data set and add them together. So I would take 90 plus 94 plus 89 plus 85, 89, 90 plus 80, 85, and 88. To get my total grand mean. So I'd add all of those together and divide by 9. So my total grand mean is 87.78. I'm going to put this here because we'll use this in just a moment. So next I want to calculate my degrees of freedom within, my degrees of freedom between. I could calculate my degrees of freedom total if I was concerned. So my degrees of freedom within. I would look at my total sample size, which is 9, and I would subtract, if you'll look in the slides, it says subtract K, which is the number of groups. So we have 9 total participants, we have 3 total groups, so 9 minus 3 is 6. My degrees of freedom between is my number of groups, or K, minus 1. So we have 3 groups total. 3 minus 1 would give us a degrees of freedom between of 2. So my degrees of freedom total would just be 6 plus 2, which would be 8. But we're going to really use these two values here. All right, so my sums of squares within and my sums of squares between. In order to calculate these, what I'm going to do is to add some extra columns here for some of these calculations. And finally, one more. All right. And so what I'm going to put in these columns are my calculations for x minus the mean of that group squared. So x minus the mean, and we're going to square that. And so you should, at this point, be fairly familiar with this calculation, right? So x minus the mean squared. So I take each of these values within the group, subtract the group mean. So I take 90 minus 91 and square that. And squared would give us 1. 94 minus 91 squared would give us 9. And finally, 89 minus 91 squared would give us 4. And we're going to, then we're going to sum all of that together for that group. So that would give us a sum of 14 for that group. Then I would take my 85 minus my group mean for this group of 88. And I would square that to give me 9. 89 minus 88 squared would give me 1. And then 90 minus 88 squared would give me 4. And so I have a summed squared deviation here of, again, 14. This one will have some decimal values, but we'll take 80 minus a group mean of 84.33, square that to give us 18.75. 85 minus 84.33, square that to give us 0.45. And finally, 88 minus 84.33 squared to give us 13.47. And then again, I would sum all of these together. To give us 32.67. So these right here, my summed squared deviations, are what is important. And so my summed squared deviations, we talked about my sum of squares within. And so I'd want to add all of these three values together. So 14 plus 14 plus 32.67. So it would have a sum of squares within value of 60.67. Okay, to calculate the sum of squares between, this is where we're going to use the grand mean that we calculated earlier. So essentially, what we're doing is we are again taking the sum of squared deviations, but this time we're looking at the deviation between each of our group means and this grand mean that we've calculated. So we would take our group mean of 91 and subtract our grand mean of 87.78. And we would square that value. So we would take 91 minus 87.78 and square that, which would give us 10.37. But what we want to do before is to multiply it by the number of participants, or here the number of students that we have in that group, which is 3. So I take my 10.37 and multiply it by 3 to give me a value of 31.11. Put that here, 31.11. And so I do that for each of my groups. So for the next one, we had a group mean of 88. So we would take 88 and subtract 87.78. We'd square that to give us a value of 0.05, but we would first multiply that again by 3 because we had 3 students in this group. And so that would give us a sum of squared deviations for that group of 0.15. And then finally, I would take my 84.33, subtract my 87.78. I would square that, and then again multiply by 3 because there were 3 students in this group as well. So that would give me 35.71. And so think about what we're doing here by taking each of the group means and subtracting the overall grand mean. Right? This deviation is telling us, well, how much does each group mean deviate from a grand total mean for all 9 students? So we're essentially saying which is a better way of representing this data. Should we look at this as one group of 9 students, all represented by a single mean value, or is it better to look at this as 3 distinct groups, each with their own mean value? Right? So that's kind of what we're doing here. And so we want to take each of these values and add them together. So I'd want to add together my 31.11, my 0.15, and my 35.71 to get my total sums of squared between value. So if I do that, 31.11 plus 0.15 plus 35.71, I would get a final sums of squared between value of 66.97. If I wanted my sums of squared total, I would simply add these two values together, my sums of squared between of 66.97 plus my sums of squares within of 60.67. But what I'm going to jump to is calculating my mean square within and my mean square between. So for my mean square within, I want to take the sum of squares within value that I calculated of 60.67 and divide it by my degrees of freedom within of 6. So I would take my 60.67 divided by 6, which would give me a mean square within value of 10.11. My mean square between would be a similar process. I would take this sum of squares between value of 66.97 that I calculated and divide it by my degrees of freedom between of 2, which would give me a value of 33.49. And then finally, to calculate my F-test statistic, all I'm going to do is to take my mean square between value of 33.49 and divide it by my mean square within value of 10.11. And so think about what we're doing. Just like we did before, for our final test statistic here, our F test, just like with our t-test, we have a ratio of variation between groups to variation within groups, because what we want to say is that these groups are varying more between groups than scores are varying within each group. So this is giving us that ratio. So my between group variation is 33.49. My within group variation is 10.11, which gives me a final F test statistic of 3.31. So I want to compare this value of 3.31 to my F critical value, the value that I obtain from an F table. So let's do that now. Okay, so we know to use our table. So here we're looking at the cutoff scores for the F distribution. Right? We've calculated an F statistic. We want to get our critical F value. That we need to know our significance level and our degrees of freedom. This table is a little more complex because we have two measures of degrees of freedom. So remember that we calculated a degrees of freedom within and a degrees of freedom between. So our denominator degrees of freedom, they're degrees of freedom within. And so we calculated that to be 6. Our numerator degrees of freedom is our degrees of freedom between. We calculated that to be 2. So we want to look at this column and this row, but specifically you see that we have our significance levels of 0.01, 0.05, and 0.10. So we want to use the 0.05 level for 6 and 2 degrees of freedom. So our F critical value, or our cutoff value, is 5.14. We calculated our F statistic to be 3.31. So that is lower than our tabled or critical value. And so we would have to retain the null hypothesis. We'd have to conclude that based on our data, there was not a significant difference between the group means amongst the 3 instructors. So I couldn't make the case that I am a significantly better instructor, or that my students, based on this data, are scoring or getting significantly better grades than other instructors.